Hi guys, I hope all of you doing well. Here we are going to analyze JAM 2020 chemistry problems. I can say you may have number of videos on JAM 2020 chemistry on YouTube. So here you will get the best analysis with extra information from each and every problem. That's why watch the video completely. Now, if you are interested, just visit chemmasters.online and join the best courses for JAM chemistry. Now, just look at the given problem. The correct order of boiling points of compounds 1 to 4. So just observe the given compounds. So by just observing the given four compounds, we can say we have given with two types of compounds. One type is alcohol and another one is ether. Okay, right. In general, when you observe alcohols and ethers, alcohols will have higher boiling points when we compare with ethers. Can you say the reason? Or do you know the reason of it? So we can simply say that alcohols will make hydrogen bonding among themselves. Okay, so due to the formation of hydrogen bonding in alcohols, boiling points are normally higher than ethers. When you observe ethers, ethers cannot make hydrogen bonding among themselves. That is just lacking of hydrogen. Okay, right. But ethers can simply make bonding with proton whenever the availability of hydrogen in that particular reaction media. So we can say here ethers can only act as proton acceptors. Okay, hydrogen acceptors, but here ethers are not going to act as proton donors to make hydrogen bonding. So, due to the lacking of hydrogen bonding formation in ethers, ethers are having less boiling points when we compare with alcohols. Okay, this is the basic concept. Just remember. So, from this point, we can say the second compound should have least boiling point among the given four compounds. So, just look at the two here options. We can say answer must be in option C or option D because here the second compound or ether is given with the least boiling point. Okay, right. Now just look at the given three alcohols 1, 3 and 4. Now just remember that whenever you see higher N alcohols, okay, higher N alcohols will have higher boiling points. Okay, so that is given here 1 and 1. Now just look at third and fourth by that simple concept, that is higher N alcohols. When you observe third and fourth, you can see higher carbons in the third one. So this one should have higher boiling point when we compare with this branched, so directly our secondary alcohol. Okay, so here the correct order must be in option C. Okay, so this is the one kind of analysis we can apply on it. If you observe general boiling points among all alcohols from methanol, you can see the correct trend or the general trend may not be observed. So many factors are involved in it. So just check that means the concept lecture on alcohols. Okay, right. Now just look at the next question here. The d orbitals involved in the hybridization to form square planar and trigonal bipyramidal geometries or respectively. Now try to look at square planar. So try to draw a square planar geometry. Okay, right. We can say it is just consider Z, and that means orbital is, that means d orbital along Z axis. Okay. Now here we can say so x axis, and here just say y-axis. Okay, so here the d orbitals along x and y, right? And the ligand approaches along x and y to make hybridization. So that's why here we can say that whenever the d orbitals of that particular metal and the electrons of ligand approaches from the same direction, or that means on same line or same axis in opposite way, there is the repulsion can be seen. Okay, so due to that repulsion the energy rises. So in square planar geometry the highest energy d orbital must be dx square y square. Okay, right. And then here you can see, so the least energized d orbital must be from that z-axis only, because there is no orbital observed along that that means no ligand approaches can be seen along this z-axis in square planar geometry. Okay, so that's why here we can say next one dz square. At the same time, so here you can see in between the x and y, so ligand approaches from here. Okay, so with the least energy we can say dyz dxz. So this is the energy levels of the d orbitals in square planar geometry. So highest energy with dx square y square, which is going to be involved in hybridization. So here for square planar it must be dx square and y square. Now just look at trigonal bipyramidal geometry. So simple, we can represent it is, that means a d orbital along the z axis. So along the z axis, ligand approaches the orbitals of that particular metal. Okay, so that's why highest energized orbital is dz square in that particular trigonal bipyramidal geometry. Okay, the next one will be dx square y square and dxy here. Okay, just write it dxy, and least energizer will be dyz and dxz. Okay, so this is the energy order of the d orbitals, right? And here dz square involves in hybridization, so answer must be option C. Okay, right. And next question here, just look at the graph that represents the temperature entropy variation of Carnot cycle, right? And here TS diagram, that is temperature entropy diagram, used to visualize changes to temperature and specific entropy during a particular thermodynamic process. That is, here TS diagram used to visualize heat transfer. Okay, used to visualize heat transfer during a thermodynamic process. And here we can say TS diagram is icentric. Okay, icentric and isothermal process. Okay, TS diagram in Carnot cycle is icentric and isothermal process. That's why here we can simply choose option B, where you can observe, so that means square of this graph, which is indicating icentric and isothermic, and option B is our answer. Okay, right. And next question here, the salt bridge in a galvanic cell allows the flow of. So here we can see salt bridge is an inverted U shape. Okay, so here we can simply say that inverted U-shaped tube filled with concentrated solution of inert electrolytes. Okay, so whose ions neither involved in any electrochemical changes nor do they react chemically with the electrolytes in the two half cells. Okay, so here the salts may be used as KCl, KNO3 and K2SO4, etc. Right? Here gelatin, so this is the extra information about salt bridge. Gelatin and agar-agar is dissolved in hot concentrated aqueous solution of an inert electrolyte in that particular solution. Okay, right, here ends of U-shaped tube or simply plugged with cotton or wool as to minimize diffusion effects. Okay, so what are the main functions of salt bridge here? So simply it connects the solution of two half cells and complete cell circuit. Okay, right. And salt bridge prevents transfer or diffusion of solution from one half cell to another half cell. and it keeps solutions in two half cells electrolytically neutral by just moving. So cations here tilt towards anions of the solution and anions tilt towards cationic solution, the two half cells. So that means what you are just observing, ions will move in the salt bridge, not electrons. Okay, so just look at the given options, ions but not electrons. So salt bridge in a galvanic cell allows the flow of ions but not electrons. So here our option is A. Okay, right. And just remember that salt bridge prevent liquid, okay, prevent liquid junction potential. That is the potential difference which arises between two solutions when contact with each other. So that is the main function of salt bridge. Okay, just keep that important point in your mind or just note it. And next question, for the radical chain reaction below, the correct classification for step 2 and step 3 respectively. Let's just look at the step 2 and step 3 here. So bromine radical, whenever reacting with molecular H2 or hydrogen producing HBr, okay, I am producing radical hydrogen ion which is going to react with bromine molecule and producing HBr and bromine radicals. So these radicals are again and again possible to involve to make in the making of HBr. Okay, so that's why we can simply say that these two steps are called as propagation steps. Okay, so chain propagating and chain propagating in step 2 and step 3. So option C is the correct answer. Okay, now so just try to look at the basic chain reactions can when we see here bromine reacting with M. Here M can be considered as radical initiator. Okay, produces bromine radical, right? And this bromine, and we can consider this step as radical initiation step. Just note it. Okay, and second step, the released bromine radical reacting with H2. Okay, that is molecular hydrogen producing HBr and hydrogen radical. We can consider it as propagation step. Okay, and third step, the hydrogen radical react with bromine molecule produces HBr and bromine radical. So we can consider it as propagation step. And in further, the fourth step we can consider hydrogen radical whenever reacting with HBr produces H2 plus Br radical. We can consider it as termination step. Okay, and whenever two bromine radicals react to produce bromine molecule, we can also consider it as termination step. Okay, so here our answer is C. And next question, the nucleobase not found in DNA. So first thing, nucleobases. Here we have two kinds of nucleobases. One is pyrimidines. One type is pyrimidines and second type purines. Okay, so here pyrimidines containing cytosine, thiamine and uracil. Okay, so cytosine, thiamine are generally absorbed in DNA, whereas in cytosine and uracil absorbed in RNA. Okay, so this is the difference we can observe. Uracil is absorbed in RNA, thiamine is absorbed in DNA, and all other absorbed in DNA and RNA. Okay, so this is the difference. If you remember, you can simply give the answer. So the nucleobase not found in DNA is uracil. You can observe thymine, guanine, and adenine. So where we can get guanine and adenine? So simply from that purine. So purines containing adenine and guanine. So adenine, guanine are just common in DNA and RNA. Okay, right. And here just look at pyrimidine bases. So in it, that means the name in itself is having its heteronuclei, that is, so simply pyrimidine structure. So just try to draw the pyrimidine structure here. So this is the pyrimidine structure of cytosine. So NH2. Here we can consider it as cytosine. Now, and next one, thiamine. So same, just do the two nitrogens here, and here double bond O, here double bond O, and here CH3. So we can consider it as thiamine. Okay, and now you can see uracil. So here we have uracil structure, right? So this is about uracil, right? And next, pyrimidines, right? Here pyrimidines are simply the fused heterocyclics. One structure is pyrimidine, okay, and another structure you can see. So 5-membered ring, here double bond, here NH2, okay, right, and that is adenine. Just note down adenine. And the next one, guanine. Here you just write down C double bond O, NH2 double bond. Here is a double bond. Sorry, not double bond. So just make it complete structure of it, right? And this is about guanine. Okay, right. And how to give the numbering on these pyrimidines and purines is very important. Okay, so just try to give numbering on the heterocyclics of pyrimidines and purines. From that you will get extra, other means you will get the extra information to solve the number of questions. Here I can ask you one question, that where that means DNA, nucleobases or purines will connect or makes a bond with cisplatin. Do you know the importance of cisplatin? So just try to check its function. Okay, so here we may give, already we have the question in CSIR, that is that means N9 or N7, like that. So which nitrogen will connect with cisplatin? Okay, and which nitrogen will connected with here we can say 5-membered ring. Okay, 5-membered carbohydrate ring with the phosphate in a DNA structure. So just try to check all of them for your competitive purpose, and if you are interested, just visit and join chemmasters.online for the best concept oriented courses for guaranteed success. Thank you very much.